All right, so to summarize where we ended up in the last video, right, work is equal to a net force that causes displacement. Work equals force times displacement, right? So work is done when a net force causes displacement. Okay, an added caveat, right, is F net must be parallel, right, using the math symbol for parallel. F net must be parallel to the direction that the object is being displaced. Okay, net force causes displacement. That net force is parallel to displacement. And so the entire force doesn't necessarily have to be parallel to the displacement, but there must be a component of the force that's causing displacement. All right, so again, we've got work equals an unbalanced force times displacement. We can do several things here. And force, we can write as MA, F net equals MA, right, times displacement. And what is that displacement caused by? It's caused by a net force, right? And that net force causes acceleration, right? You're going to speed up or slow down due to that net force. So we've got our energy equation, work equals force times displacement. And net force we can substitute in Newton's second law, right? F net equals ma. And then for distance or displacement, since an object is accelerating due to a net force, let's try and play around with a motion equation. Why not, right? So if we're accelerating, speeding up, okay, and then let's do some algebra here. V final minus squared minus V initial squared over 2 equals AD, right? So what if we actually instead, right, MA is force, but if we take this AD and we plug this in for it, then we would have M times V final squared minus V initial squared over 2 equals FD, which is also equal to work. Let's simplify this one step further. This factor of 2 is a 1/2. It applies to everything. So we can waive our algebra 1, and what we end up with here is a more familiar equation, 1/2 m v final squared. Okay, and then minus 1/2 m v initial squared. Okay, that's what this simplifies to. I don't need to box that. I just wanted to bring your attention to it. So here we can say work is equal to a net force times the displacement that net force caused. And that's equal to 1/2 mv final squared minus 1/2 mv initial squared. What is 1/2 mv squared? We just talked about that just a moment ago. That's kinetic energy, right? So we could write this as kinetic energy final minus kinetic energy initial, right? Kinetic energy final, kinetic energy initial, and they're being subtracted. What's one way that we can summarize what this is called? A final anything minus an initial anything? We call that the change in kinetic energy. The change in. Final minus initial is always the change in. So if we write this in its most abbreviated terms, work is equal to a net force times the displacement that it causes, right? Net force causes objects to speed up and slow down, so they will be accelerating, their kinetic energy will be changing. All right, so I'm going to box this and this as the more abbreviated version. All of those terms are equivalent to each other. So how much work is done? You can calculate that by multiplying the force times distance. How much work is done? You can find the change in kinetic energy. If a problem gives you the change in kinetic energy, that's how much work is being done. Okay, so they're all equivalent. And yes, I did box these on purpose. These guys should be in your equation sheet. The derivation doesn't need to be included in your equation sheet, but these two guys are what you want. Okay, what does the work energy theorem have to do with anything? By the way, that's what these two guys are called, is the work energy theorem. And this is probably one of the most important theorems in terms of physics informing public safety measures. So let's take a look at forces in car crashes. Okay, so this might not be a realistic example, but it was some clip art that was easy for me to grab. And so we've got a car traveling a speed of about 31 miles an hour, so kind of slow, almost school zone or neighborhood speeds. And that's 14 meters per second. Okay, so then the car crashes into a tree. And the driver fell asleep, swerved off the road, crashed into a tree. So that's tells us, without explicitly saying it, that the car's final speed is 0. And so this is the initial speed, 14 meters per second. The car itself has a mass of 1,450 kilograms. It's about 3,000 pounds. So this car is kind of a boat. And then it wants to know the initial kinetic energy. What's the final kinetic energy? KE final is 0. Because the car stopped. Yeah, okay. The initial kinetic energy is 1/2 this mass, 1450, times its initial speed, 14. And that's 14 itself is squared. So KE initial is 14 squared times 1450 divided by 2 is 142,100 joules. So the work required to stop the car, remember, we don't have any information about force and displacement, but work is the change in kinetic energy, which is kinetic energy final minus kinetic energy initial, right? And our final kinetic energy is 0 minus our initial kinetic energy is 142,100 joules. And so the amount of work that's done is negative 142,000 32,100 joules. Wait, Miss McVeigh, I thought you told me energy wasn't a vector. It's not, but in the work energy theorem equation, there exists a force, right? It is a vector. And it's not like, we're not talking about, still it's not really direction, kind of is. The force value would be positive if the net force being applied is speeding up an object. The force would be put in this equation as negative if an object is slowing down, right? So for us to get a work value that's negative, it's meaning the force that is applied to an object is opposing motion. Okay, that force is slowing an object down. Okay, so the work, right, we're losing kinetic energy. I think losing is just 1O. We're losing kinetic energy. The force is opposing motion. All right, now here's the thing. We know how much work is done. What is the force? What is the force? The stopping distance here is 1 meter. We can assume the driver, again, has fallen asleep at the wheel. They did not apply the brakes. The stopping distance represents the distance that the hood of the car crumples upon collision. Okay, and the force that's being exerted on the car is the force of the tree pushing back on the car, opposing its motion. Okay, so the distance is 1 meter. Well, what a piece of junk of a car, right? The hood crumpled a whole meter. It's actually part of the safety mechanism. If you open up the hood of a car, if you look in there, you'll probably actually see a lot of empty space. I can often see the ground when I open the hood of the car, like look down and you can see the driveway down below. There's empty space built in for this reason, for the reason of physics. It's called a crumple zone. And this activity, as we work through it, will show you why it's important to have a crumple zone, to have airbags, and to wear your seatbelts properly according to the work energy theorem. Okay, so let's take a moment. How about you try this first calculation? Calculate the force, right? Take that work value that we just calculated, a distance of 1 meter, calculate that force from the tree that is causing an object to stop, and then convert the value from newtons into pounds just to have some perspective about like what that would feel like in a unit that we have some like inherent conceptual understanding of. All right, I'll be right back and we'll check your answers. Easy math, right? Divide by 1. So the force applied is negative. It's opposing the motion of the car. It's the force applied by the tree on the car to slow it down. 142,100 newtons of about 32,000 pounds of force. Okay. What I would like you to do now is to take a look at this scenario on the back. Instead of looking at the car, the force exerted on the car, take a look at the force exerted on the driver, assuming that they're 70 kilograms, which is about 150, 160 pounds. Okay, in 3 scenarios. Non-stretching seatbelt, right? When your seatbelt is ratcheted down and locked down and you can't move, your stopping distance would be exactly the same as the distance the car is stopped. If you're not wearing a seatbelt, your stopping distance is 20 centimeters, which is the distance it takes for your spine to crumble or your neck to roll or whatever. And then if your seatbelt stretches like it's supposed to.